So this presentation is a simulation of the loaded characteristic of a separately excited DC generator using Multisim. So the objectives of the simulation or this activity are to record the external and the regulation characteristics of a separately excited DC generator and to determine the conventional efficiency of the separately excited DC generator. So we'll be using the circuit constructed from the previous experiment. So but this time we try to add a load at the terminals of the generator, and then we will try to examine the properties of the DC generator under loaded condition. So in the same setup, so we have on the left side the prime mover of the DC generator. Okay, so and then we have in the right side the separately excited DC generator, and then we have here the virtual load of the generator, which is actually a lamp. And then we try to measure the voltage across the terminals of the DC generator using a voltmeter, and then we try to uh, measure also the output current delivered by the generator to the load. So along in the experiment, so we try to vary the power consumption or the wattage output of the virtual lamp, and then we'll try to examine how the generator react with the change in the wattage of the load at its terminal. So assuming that you have already performed the excitation characteristic of DC generator, so we uh, will try to open the save circuit, and then we'll try to construct the given circuit diagram in order for us to gather the data for the this particular activity. So this would be the machine parameters, which is the same as with the previous activity. So this would be for the prime mover, and then this would be for the uh, DC generator. So uh, we are asked to fill in the following data. So the field excitation current, the load current, the terminal voltage. So with respect to the different wattage of the load, and at the same time we try also to calculate the following data. Okay, so for the second table. So assuming that we have already or assuming that you have saved the circuit from the previous activity. Okay, so we open. Okay, so if this is the first time you open the multi-sim, so the validity of the installed software will be 7 days. Then you will be asked to uh, extend the activation of the multi-sim. Okay, so all you need to do is to create an account. So in the National Instruments website, and then after creating, you open again the multi-sim software, and then you'll be prompted. Okay, so you'll be prompted that the evaluation period of your multi-SIM was already extended. So the extension will be around 45 days. So that is exclusive from the 7 days trial evaluation. Okay, so in uh, this case, the last activity, which is the excitation characteristic of this generator, the circuit was saved. So we try to open the circuit. Okay, so we click launch multi-sim. Okay, so this was the circuit uh, coming from the previous activity. So if you haven't saved the circuit, you may go back to the previous activity on how to construct the given motor generator setup. So first we try to we try to fit all the um, elements. Okay, so we can so can move this one is together with this one. Okay, so we'll try to create a room for the additional meters and the load. Okay, so we'll try to construct again. Okay, so then okay, so for the generator, okay, so you need to connect the shaft of the prime mover to the shaft of the generator. So again, if you have already saved the circuit from the previous activity, you don't need to redo the same circuit. So all you need to do is to open. Okay, so okay, so and then we try to add a load to the terminals of the uh, DC generator. So we'll try to delete first the lines is of the generator. Okay, so then we insert the virtual lamp as given. Okay, so this is actually the circuit diagram that we need to construct in multisim. So we need to find the virtual lamp. Okay, so this will be used as the virtual load of the DC generator. Okay, so click place basic. Okay, and then in this tab, click all groups. Okay, so once you have already the all groups, so just scroll down. Okay, so scroll down and then choose virtual lamp. Okay, so this one virtual lamp, click OK. So you may click it anywhere and then click close after. Okay, so this would be the electrical load of the generator. So kindly right click and then rotate 90 degrees clockwise. Okay, and then you will have there the vertical position of the um, virtual lamp. Okay, so this lamp will be supplied by the voltage generated by the generator. Okay, so the terminals of the generator. Okay, first we need to have the ammeter first. So the ammeter, which is used to measure the current flowing into the load of the load, which is the virtual lamp. So double click this one and then click ammeter. The straight line represents DC. Then you may close the meter, then connect. Okay, so connect this terminal to the ammeter, one end of the ammeter. Okay, so you may move it upwards. Okay, and then the other end of the meter will be connected to the load. Okay, so you can connect it, or you can drag it upwards. Okay, and then one end of the generator is will be connected to the other end of the lamp. Okay, so the voltage generated by this generator will be supplied to the lamp. Okay, so now we need to measure the voltage across the lamp. So we connect the voltmeter in parallel with the lamp. Okay, so we can click. Okay, so the positive terminal of the voltmeter, okay, to be connected in one end of the lamp, and then the other terminal of the uh, voltmeter will be connected also to the other end of the, or the other terminal of the lamp. So there we have the loaded generator. Okay, so we try to see if the parameters are the same as with the given. Okay, so the parameters are, for the motor, is a double click motor rated, and then you will have the, okay, so the parameters, so animation factor 5, 200, 208, 200, 1.11 milli. Okay, so and then okay, everything is the same as with the given table for the generator. So we try to double click and then go to the next. Okay, so next slide for the DC generator. So we'll try to examine the 0 0.1, 0 0.2, 500, and okay, so everything is the same as with the given parameters of the DC generator. So click OK. Okay, so then we go to the lamp. Okay, so for the lamp, so double click the lamp and then type 250 volts as the maximum voltage that can be given to the lamp. So this is the rated voltage of the lamp. So the rated power of the lamp will start with 0 first. Okay, so I mean 10. Okay, so 10 watts. Okay, so this would be, okay, click OK, and then we are already ready to simulate the loaded characteristic of the DC generator. So the ammeter 1, you can double click to display the reading. Okay, so ammeter 2 also. Okay, so and then you have there the voltmeter. Okay, so multimeter XMM3. Okay, so meter 1 and meter 2 are ammeters, whereas meter 3 is set as voltmeter. Okay, so meter 1 measures the current taken by the load. Meter 2 measures the excitation current or the field current. So this field current is the one responsible to create the magnetism in the poles of the generator. So you remember that for a generator to build or to generate a voltage, the generator must be given with mechanical energy plus the magnetism. So that would equate to electrical energy in terms of voltage at the armature terminal of the DC generator. Okay, so we try to look at the table. Okay, so these are the uh, data that you need to fill in. So the excitation current, the load current, then the terminal voltage. On the second table, so you have there the load current, terminal voltage, the power output, the torque, the speed in radian per second, the power input, and then the efficiency of the machine. Okay, so try to look at the first table first. Okay, so then we try to simulate. So we run the simulation. Okay, so before that one, so you double click the field resistance R2. Okay, and then make the increment to be 0.1%. So that means the increment in terms of the ohmic value would be zero point 0.1. So for example, you start with 0, the next value would be zero point 0.1, zero point 0.2, zero point 0.3, zero point 0.4, and so on. The maximum value of the potentiometer is 1000 ohms. Okay, so click OK, and then we are good to go with the simulation process. So click this one, the run button, or press F5 in your computer. So once you click this one, so you will have there the current. Okay, so taken by the okay, so the meters, and then the ammeters, and then the terminal voltage of the generator. So if we try to look at the table, the first table, so the load in watts. Okay, so the load in watts will start with 0. Okay, so meaning to say that there must be no load. Okay, so no load voltage, no load resistance, so that means 0 watts. So we need to stop the simulation first. So for 0 watts, we need to disconnect first the load. So this should be the setup. So as you can see, the load is not connected to the generator. So you may leave it there as hanging and then run the simulation. Okay, so we need to maintain a voltage of 200 volts at the generator terminals. Okay, so to adjust the voltage, so we need to adjust the excitation current, so the strength of magnetism. So you need to click here and then find a value. Okay, so until you can have the voltage at the terminal, which is 200 volts. Okay, so can drag it down. So and then you have there the voltage reaches 200 5.083. So you can adjust further. Okay, so for simplicity, you just need to click this one, click, and then use the arrow keys, the arrow keys in your computer. So you press the arrow key to the right, and you notice that the percentage of the potentiometer value changes. So we need to generate, or we need to have a generated voltage of 200 volts. So continue to, okay, so continue to press the arrow keys. So you may press the arrow keys to the right or left. So until the generated voltage should be 200 volts. Okay, so the voltage. Okay, so again, when you press the arrow keys, make sure that you click this tapping of the resistor or potentiometer. So just like that, so you can increase or decrease. So find a value until the voltage should be approximately equal to 200 volts. Okay, so you have there at 35.9%. Then the output voltage is 199.965, or basically exactly 200 volts. Okay, so uh, we gather the data. Okay, so by filling up the table. Okay, so for the 0 watts load. Okay, so for the 0 watts load, so the excitation current, which is measured by the, okay, so the excitation current, which is measured by meter 2. Okay, so we'll have a value 155, okay, 0.982. So in milliampere, milli means times 10 to the power of -3. So the load current is measured by multimeter 1, so 200.018 nanoampere. So that's, okay, so nano is times 10 to the power of -3. So nano means times 10 to the power of -9. Okay, so the terminal voltage at no load is 200 volts. Okay, so then next is the load wattage for the virtual lamp is set to 20. Okay, so 20 ampere, 20 watts. Okay, so that's 20 watts. So you need to stop the simulation first, and then connect the virtual lamp to the terminals of the generator. Okay, so for it to be supplied with the voltage. Okay, so double click the lamp and then change the wattage to 20 watts. Click OK and then run. So this time you have now a difference in reading. Okay, so we have there for meter 1. Okay, so meter 1 will measure the Okay, so meter 1 will measure the load current. So this time, okay, so the load current is equal to, okay, so that's 63.985 milliampere. 63.985 times 10 to the power of negative 3 ampere for the field excitation current. Okay, so you have there for meter 2, so that's 155.982. Okay, so milliampere, and then the terminal voltage is 199.952. Okay, so then we change the wattage of the load to the next value. Okay, so we stop the simulation, then okay, so double click, okay, double click this one, change this one to 40 watts, click OK, and then run. So you notice that the, okay, you notice that the voltage, there is a slight change in voltage, and then the current also increases. Okay, so we record. Okay, so the, okay, meter 1. Okay, so meter 2 is for the excitation current. So you notice that there is no changes in the excitation current. Okay, so for the load current, so as you can see, as the wattage of the load increases, the load current also increases. So that would be 127.961 milliampere, and then the terminal voltage is 199.939 volts. Okay, so you'll be tasked to continue gathering the data for the rest of the load wattage of the virtual lamp. Okay, so next is we go to the, okay, so we go to the second table. Okay, so you have there the load current, the terminal voltage, and then the, okay, output power, torque, speed, power input, and efficiency. So we copy the load current, might as well the terminal voltage. Okay, so from the first table for the first three. Okay, so for the first three uh, data, is for the first three data of the experiment. So they would be the same in the, okay, so type this 12, then 10. Okay, so we can, okay, so load current, so the power output, okay, so the power output of the generator is equal to, okay, so the power output of the generator is equal to the product of the current and the terminal voltage. Okay, so for the output power, so you need to multiply. Okay, so for 0 watts, so you have there 200.018 nano. Okay, so -9 times 200, so that will give us power output of 4 times 10 to the power of -5 watts. Okay, so we'll try to, okay, so 10.5. Okay, so that's 4 times 10 to the power of -5 watts, or that's 0.00005. I mean 4. So for the 20 watts load, so take note, this load in watts is the load uh, maximum wattage in the virtual lamp. So this does not mean that this is the power output of the uh, DC generator. So it means that uh, we try to increase the load wattage of the lamp, and then we try to examine what happens to the generator. So once we try to increase the wattage of the connected load. So for the 20 ampere, so we can, I mean for the 20 watts, so we can multiply the voltage and current. So that would be 63.985. Okay, so milli, and then times 199.952. So you have there 12.79. So the answer is watts. So obviously, if you try to look at when the load is 0, that means if we try to remove the virtual lamp from the generator, okay, so this one, if we try to remove the virtual lamp from this generator, okay, so let me do it again. Okay, so click and then delete. Okay, so delete, click this one and delete. So you notice that the generator is actually supplying no load. So the current measured by the, okay, so the current measured by the meter 1 is around 0 ampere, because no load actually, uh, there is actually no load at the terminals of the generator, hence the current is 0. However, since there is a voltmeter connected to the generator terminal, so the internal resistance of the voltmeter, so actually is the one that draws current from the generator. So let's say if we try to remove the voltmeter, or if we try to disconnect the voltmeter, we will see that the current, okay, so we try to simulate again. So we will see that the current actually is 0. Okay, so you have the 0 ampere, which means that no load is drawing current from the generator. So the 200.0018 nanoampere actually is the current drawn by the voltmeter. Okay, so due to the internal resistance of the meter, so which is very high, so that's why it draws little amount of current. Okay, so we continue. Okay, so for 40 watts up to 150 watts, so you will be tasked to complete the data. Okay, so in this table, so next is we try to measure the torque and the speed. Okay, so these parameters, the torque and the speed, are needed to calculate the input power of the generator. Take note that the generator is a machine that converts mechanical into electrical energy. So meaning to say, the input of the generator is mechanical. So if you try to look at in this setup, so this generator is actually being uh, commanded, or it is actually being rotated by the prime mover or the shaft of the prime mover. So no electrical input is given to the generator. So the electrical input here, the 100 volts DC, which is actually injected in the field, is used to create the magnetism. So the main input of the generator is the mechanical force coming from the shaft of the prime mover. So to measure the torque, okay, so you click this ammeter current. Okay, so ammeter, and then okay, so press escape first and then stop the simulation, then click this one. Okay, so current, or actually this is an ammeter, but we will use the data for this ammeter to represent the torque. Okay, so provided by the prime mover to the shaft of the generator. So click this one and then point it to the connecting line between the motor and generator. Okay, click. Okay, so you may adjust it anywhere in the working area. To measure the speed in radian per second, we need to click the voltage. Okay, so this one, the voltmeter. Okay, so this measures actually voltage, but we will use the voltage to represent the speed in radian per second uh, in the shaft of the prime mover. So click this one and then point it to the line connecting the motor and generator. Click. Then you may adjust it to anywhere you wanted in the working area. Okay, so take note the unit of the speed, okay, so is in radian per second. Although the measurement will give you volts, so just omit the volts and replace that with radian per second. For the clamp meter, so you need to ignore the ampere unit. We replace that one with Newton meter. Okay, so we need to, okay, so for 0 watts, okay, so first we have to have 0 watts. That means we need to disconnect the load. Okay, so try to delete this one first, disconnect the load, okay, and then simulate. Okay, so we have the following data for the torque and the speed. For the speed, so you refer to this reading. So let me zoom it out. So that's, I mean, for the torque, no? So you refer to this reading, that's 2.56 milli. So you ignore ampere, you replace this one with Newton meter. Okay, so this would be 2.56 times 10 to the power of negative 3. So unit in Newton meter. Okay, so meter. And the speed is 2.56 kilovolts. So you replace volts with radian per second. Kilo means, okay, so kilo means times 1000. Okay, so this would be 2560. So radian per second. Okay, so for the 20 watts load, okay, so the 20 watts load, so we now connect the virtual lamp. Okay, so you can use the scroll button in your mouse to zoom in and zoom out the working area. So we stop the simulation first, and then we connect the lamp to the terminals of the generator. Okay, so this one, okay, connect it to this terminal, click. Okay, so and then make this to 20 watts. Okay, 20 watts, and then uh, you run. Okay, so you notice that the torque of the machine, or the torque of the generator or the motor, increases. So this is what will happen to the prime mover. As the load of the generator increases, the input torque, okay, so to the generator will also increase. So in this setup, the voltage of the, no, not the voltage, but the speed of the generator is being held constant. Okay, so such that the terminal voltage of the generator will also be around 200 volts. So although there is a sudden, a minor drop, but that's negligible. Okay, so you may observe that the terminal voltage will somehow drop with a very minimal value as you try to increase the uh, wattage of the virtual lamp. So in the table, okay, so this is for 20 watts load. Okay, so the torque measured is, okay, so as given. So we can zoom out. So that's 7.55 millinewton meter. So not milliampere, times 10 to the power of negative 3. Okay, so unit in Newton meter. And the speed is 2000, still the same, 2560. Okay, 2.56 kilo radian per second. Okay, so again, for the rest of the data, in the table, so you'll be the one to perform and gather the following data for the torque, power, and efficiency for 40 watts load up to 150 watts. Okay, so the power input, okay, so the input or the mechanical input of the DC generator can be calculated using the formula. Okay, so the input power can be calculated using the formula 2 pi. Okay, so the input power is equivalent to 2 pi, then NT over 60. So wherein N here represents the speed in revolutions per minute. So meaning to say we need to convert the radian per second unit into RPM. So take note. Okay, so N is in RPM. Okay, so RPM means revolutions per minute. So revolutions per minute. Okay, so this should be the unit of the speed. Okay, so this one. Okay, the speed. So we try to calculate. Okay, so using this formula. So okay, so if you have your calculator, so you can type. Okay, so 2 pi times n. So the speed in RPM, okay, so that's 2560 times, okay, to convert radian per second to RPM, you need to multiply, okay, so you need to multiply it with 30 over pi, okay. So you have the 2 pi times n. So n is the speed in RPM. So since we have radian per second, so we need to multiply it with 30 over pi to convert it into RPM. So 2 pi n, the torque is 2.56 milli. Okay, so times 10 to the power of negative 3. Okay, so divided by, okay, so times, okay, divided by 60. Press equals, and then you will have, okay, so you will have an answer of 6.5536 watts as the input. So for the 20 watts virtual lamp, okay, so the input, the power input can be calculated, okay, so using the formula 2 pi nt. So we need to substitute the torque, okay. So instead of having 2.56, so we have there 7.55. Okay, millinewton. Okay, then you will have 19.328. And then Okay, so to calculate the efficiency, okay, so the efficiency would be the ratio of the output power to the input power. So for 0 watts virtual lamp, so the output power is almost zero. So, but anyway, we'll try to calculate. Okay, so that's 4 times 10 to the power of negative 5. Okay, so divided by 6.5536. Okay, so 6.5536. Okay, so this would be 6.5536. And then you multiply it with 100 to convert it to percentage. And then you will have there almost 0%. Okay, so that's 0%. Okay, so that's 0.00006%. Okay, so for the 20 watts load, okay, so this one, so we can calculate the efficiency. So the efficiency of the generator is equal to, okay, so that would be power output, that's 12.79 divided by 19, okay, 0.328, so times 100%. So the efficiency of the generator when delivering a power output of 12.79 watts is equal to 66.17%. Okay, so you will then be tasked to complete, okay, so the following data. So from 40 watts up to 150 watts. Okay, so might as well in the first table. Okay, so we have already the data for up to 40 watts. So you continue uh, for 60 to 150. Okay, so you record the, what you call this one, you record the data on a sheet of paper. Okay, so while performing, so you can save the circuit, the designed circuit or the simulated circuit in your computer for future reference. So your laboratory manual will be sent via Moodle. Okay, so you will then be asked to uh, write the report corresponding to this activity. So this would be for table number 1. Okay, so you fill up all the data in this table and then you continue. So actually the first two data for table 2 are from table 1, the load current and the terminal voltage. So they will be used to calculate the power output. So for the torque and the speed, okay, so you do it as shown in this video.